Okie dokie. So yeah, we finished up. We had an index bag. And an index bag is a bag, so it can do anything a bag can do, like add. But we're overriding the add, even though really it's just there for like that self-documenting code, where we have like a Java doc comment explaining how add works for an indexed bag. Presumably, I think like, okay, if I'm adding to an index bag and I say add at a specific index, that element makes sense. But if I don't specify an index, where should we put it? Any ideas? At the end, that's what you said at the back. It makes sense to me, right? Just kind of like an append, right? Add at this index, or add, just put it in the end, right? That's kind of like that'll work. But it'll be different than the add for the sorted bag, or ordered bits, or whatever it was called, because add won't just add to the end. I mean, it will if it belongs there, but it's going to add it where it belongs. Okay. So, inheritance. We talked a little bit about this idea of inheritance before, and it's come up a few times. It's come up in the context of, like, okay, everything inherits from the object class, meaning that you get a couple of methods for free with every object you write, like equals, toString, hash code, whatever. The ones you get for free aren't that helpful a lot of the time, so we override them with versions that we care about, like we define equality for our maze cell, for example. We've also talked about inheritance. Now that's with a concrete class, which is fine. But we also talked about inheritance with like the bag, right? Where we have a bag, but we also have a sorted bag and an index bag. They're both bags, but they're specialized, like specializations, where they have things in common, their bagness, the things that they inherit, but they have unique things. That's why they're separate interfaces in that case. So inheritance is a way to derive a class from an existing one. And it allows the ability to inherit functionality from the base class, the parent class. So imagine we had like a vehicle class, but then I wanted to have like, well, an aircraft and a bus, right? And under the aircraft, I got a 747 helicopter F-22. Under a bus, school bus, city bus, Greyhound bus, right? We could see this like hierarchy of like more abstract, more concrete, okay? It's a vehicle. Well, there's two different types of vehicles. There's going to have things in common, but they're clearly different. And these are even more specific. Having things in common with this and each other, less in common with this, but still stuff in common. You know, it's this hierarchy, all right? So in the example of the bag, well, you know, a bag, even though it's like, even though it's going to be an interface, it's still, you know, getting everything from an object. So it inherits from an object, but we have the two specializations, the sorted bag and the index bag. This hierarchical thinking exists in everyday life. However, we do need to be careful. Just because we can look at this and be like, yeah, okay, so like we have like a chair, but what kind of chair is it? Is it a dining room table chair, or is it, you know, we can play this game and categorize things and put them in these like hierarchies. And then if we start writing code, we could be like, we could become obsessed with these things in common. We can generalize and create like this superclass, and then we actually have to be very careful doing this in practice. This idea exists of inheritance, but it's important not to like over-apply it, because that often creates a lot of problems. Now we're going to go over some terminology when it comes to inheritance. Fortunately, a lot of this terminology is pretty straightforward. Like a parent class or a base class would be also like the superclass, the one on top, right? The bag is the parent class to an index bag. You could also call it the base class in that case. Or we could also call it the superclass. Superclass is another common word. And then we have the child class or derived class or subclass. That would be like, well, an index bag is a child class of the bag, right? It's relative. So like a sorted bag is a subclass of a bag, and a bag is a superclass of an index bag. An object is also a superclass of a bag, sorted bag, an index bag, yada, yada, you get it. Cool? Now the object class is always, even though in all of your classes that we've made so far, you never say like public class, maze cell, extends object. You never wrote extends object. Whether you like it or not, though, you do. Because of Java. That's just how it works. You have to. And by doing so, it adds a lot of power to our code and flexibility, things we can do. For example, if everything inherits from an object, that means every object has an equals, whether you like it or not. If you say, but I didn't write it, doesn't matter, you get the one for free. Even if it's helpful or not, it does exist. Like that type of stuff is very valuable to us. And it's important for things like the generics and whatnot as well. Because if you have a generic type of type T, I know I can still call like equals or toString on that type. Because anything that's type T must be a subclass in some way of an object. All right, so the object class. Yeah, so in Java, everything inherits from the object class. We do it automatically. Child classes inherit everything from their superclasses. This means that all the methods the objects have, we get for free, like toStrings equals hash code. However, we often override these ones for our specific functionality, right? Like equals. X dot equals y checks if x and y are equal, where like x equals y is like a sameness check. The default equals, the one we get for free as defined by the object class, is the sameness check. But we often override that to be like, okay, what does it mean for two maze cells to be equal? So a collection example. Look, if you go look at the Java collections, you're going to see this. All right? There's a class hierarchy. Now what's not shown here is the object class, which really is at the top of this. But we have iterable, which is a parent class to collection, which is a parent class to set, list, queues, and yada, 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 yada. Some of these things are interfaces. Some of them are abstract classes, and some of them are classes or concrete classes. Abstract classes are somewhere in between these two. You'll have some concrete methods, but a lot of abstract methods as well. It's kind of a nice little feature that we don't really care about right now. But there we go. There's only a few here, concrete classes. But a lot of these interfaces exist for the purpose of us implementing them for our concrete classes later. Like if I wanted to find a new collection, well, I can extend the collection or something. Or maybe it's more specific. I can extend a list or something. Pretty cool. So this is used extensively in Java, for better or worse. Abstract classes were designated. An abstract class is one that is declared with the abstract keyword. So there's a special keyword to say it's an abstract class. May or may not include abstract methods, things like the method signatures like we see in the interfaces. You can't make an instance of an abstract class. You can't. But you can create a subclass of an abstract class that you can implement. So the spirit of an abstract class is that you would extend it to define a concrete class. All right? A little different from an interface, which you implement. Sometimes these ideas get a little muddied, but it's not, don't worry too much about it. All right, so take Java's abstract queue class and its subclass priority queue. So abstract queue, priority queue, okay? You'll notice that abstract queue implements a queue, which is an interface. Abstract queue is a queue that it's not implemented. Some of the things may or may not be implemented, but not everything is implemented. You can't make an instance of an abstract queue. But you can make an instance of a priority queue that extends the abstract queue. Cool? Cool. This level of detail, by the way, is not on the test. Okay, like this is more to give you context for what we're doing. All right, so the abstract queue has several important concrete methods implemented within the abstract class, like add all, clear elements, remove. It also inherits a bunch from its superclasses as well, because there's multiple superclasses there. The priority queue class, which extends abstract queue, makes direct use of a few of these methods, like add all. But these are implemented, concrete methods. They're not abstract ones. They're concrete, actual implemented methods in the abstract queue class. And we're going to make use of a couple of these that were implemented. But the priority queue also overrides a few with special implementations. Like it's a priority queue. It's got to work a certain way. Like you would know if you've been working on the assignment. Who's been working on the assignment? Good. You should probably start that sooner rather than later. You've been warned. But you're all smart. You don't need the warning. But the priority queue also overrides a few methods like add, clear. If you open up the priority queue.java file, you will not find add all, element, or remove within it. These are the ones that we got for free from the abstract queue that were concrete methods implemented to the abstract queue. Long story short, when it comes to like extending and implementing, you might be getting some method signatures, which are just like, there's got to be a method called add. You might be getting you might be getting concrete methods, which are like, here's the method to do this. Or you might be getting like nothing and you can just add your own. There's a variation. Be aware of this. And then polymorphism. This is kind of a big deal. Polymorphism. We've been using the idea of polymorphism already, and it's an important idea. Polymorphism is the idea that the behavior can change depending on the type of the object. Though the idea of polymorphism is broader than just inheritance, mind you, this is like what we're going to talk about right here. The behavior can change depending on the type of the object. So if you look at these two examples here, okay? My stack. What is the type of my stack? Think carefully before you answer. What is the type of my stack? Who can tell me? Is it a stack? Yes, it's a stack. But, I mean, really it's a stack reference variable, but it's a stack. It's a stack, right? Now, what is the type of the thing it references? Well, here it references an array stack, which is a stack, but more specifically, it's an array stack. Linked stack, well, in this example, it would be a linked stack. So the types all still check out because this is doing like double duty. But if I were to say toString, maybe, you know what, I don't want to jump the gun. Maybe I've got an example of this, right? Let me finish through this and make sure if I don't cover the example well enough as I go, I'll come back and bring this point up. So the reference variable is for something of type stack, yet it can reference an array stack or a linked stack. This is because it is a stack, okay? Array stack is a stack, and linked stack is a stack. But it's not possible to do something like this. Array stack, I can't make an array stack reference variable and have it reference a linked stack. They're both stacks, but linked stack is not an array stack. You can go from less precise to more precise, but you can't go from like specific to a different specific. That ain't gonna work. Hopefully that's kind of obvious, all right? So you can't do that. That's because linked stack is not an array stack. By the way, if you've ever wondered, like pause on a related thing, if you've ever wondered, like, do I have to do it like this, or could I make an array stack reference variable equal to new array stack? Yeah, you absolutely can. Kind of defeats the purpose of like the interface niceness, but there's not a requirement to use the more general as the reference variable, but you could if you really wanted. It's not a rule. All right, note. Stack integer, my stack equals the new linked stack. I could do something like this because if this object's at the top, it's the most general. So I can say, well, my stack, it's an object. And a reference variable to an object can definitely reference a linked stack. You could do this. But here, the type of the thing still never changes. Okay? Like, you can't be like, oh, be very careful of what we're talking about. If I have MS is referencing this thing, that is a linked stack. Okay? The type of this is a linked stack. The type of this, it's a stack. If I then go and say object O, this is valid. It's entirely fine. Can you see this reasonably well? Let me make sure you can. This is entirely valid. You might be tempted to say, oh, so we changed its type. No, this is a linked stack. It will always be a linked stack. The type of the reference variable changed. Now, Java and a lot of similar programming languages, if I were to say O dot, it's a linked stack, O dot push, right? We know, okay, it's a linked stack. It's a stack you could push, right? If I say my stack dot push, it's fine. Okay, it's a stack. I can do that, right? Definitely. If I say O dot push, Java's going to go, I don't know. As far as I know, this is referencing an object. It could be any object. I don't know what type it is. This knows what its type is. You can ask an object what its type is, like we did in all the equals we wrote so far, right? But if I say O dot push, Java's going to go, O is an object reference variable. It could be referencing an F22. I don't think that class has a push. Maybe it does. But I don't know, right? So you got to be very careful here. The type doesn't change of the actual thing. It's fixed. Now, if you are in a case where you're like, no, but I really needed to know that well, that's when casting comes in, right? Is it a stack? Yes. Okay, cast it as a stack. That's like us saying, like, trust me, it's a stack. Java, trust me, it's fine. Yeah, you're fine. However, yeah, the type of the object itself doesn't change. You had your hand up a moment ago. You're fine, yeah? Okay, any questions so far about all that? Okay, one should be very careful though, because I just made use of this like is not a. Array stack is a stack. Note or warning, you should be very careful. This ties back to that whole thing about like, oh, we look for hierarchies in real life, so when we implement things, we always like these hierarchies. No, use inheritance carefully and sparingly. The is a metaphor can be abused and can cause a lot of trouble. Is fine in reference to the types, but not to the things they represent. More on this in a moment, but maybe not more on that in a moment. But here we go. So now there's this idea of binding, though. Look at this code. All right? This case would be called dynamic binding versus static binding. But look at this code. Presumably random number is a random number that's determined at runtime. I roll the dice. I hit run. I roll the dice. Okay? I get a number between 1 and 100. When I come down here and say print my stack, which version of the toString was called? Was it the array stacks or the linked stacks? You're right. How could you know? You can't know. We do know it has a toString. We do know it has a push because it's a stack. But the actual type of the thing, we don't know until runtime. There's this idea of compile time versus runtime. Now, if we're talking about Python, maybe it's like pre-runtime, runtime, whatever. But compile time, runtime. Compile time is, what does the program know about itself? Like, what does Java know about the program before I hit run? And what does it know as it's running? Those things can be different, right? Before I hit run, I have no way of knowing. But as soon as I hit run and we hit this line of code, it'll know. It'll call whichever one it needs to call because everything still checks out. So connecting a call, because look, I called my stack.push. The toString was called through this print, right? Those methods got called. And there's this idea of binding, where like a line of code means call this method. Well, what method? That method, right? Often we have what we call static binding, where like we know it's not going to change. We know this at compile time. But we have cases called dynamic binding, where I won't know which version of these methods to call until it's running, which is a complexity, right? Before I hit run, the computer would be very happy if before I hit run, it goes, when I get to this line, I'm going to go call the push method, which can be found on line 43 in the array stack class. Right? So when I get to that line, I just go do that one. And then, okay, before I hit run, I know where to go look. It's going to be very happy in that case. But dynamic binding is a little bit trickier because it has to go like, well, which one? We'll have to kind of find out as we go. Okay, so it's possible to get the type of, oh yeah, okay, we already did that. Cool, there we go. So pretty neat. Now, there is I've got this aside here. I'm going to go through really quickly. This is a joke, and I didn't make this joke up. It's just an existing joke. What OOP means object-oriented programmer, user claims. Like, oh, we've got this very an animal, and we've got a human, but then we have a pet, which I guess is maybe it's abstract, and then we have a dog and a cat. That's beautiful. But in practice, you get some monstrosity that looks like this. This is always what happens. This joke exists for a reason. So it's a nightmare. Okay, so don't think of the objects that we're programming. Object-oriented programming kind of made a promise back in the late 80s, early 90s, and it was all a lie. Okay? Now, the spirit of what they were trying to achieve was there. It was good. There's obviously value in object-oriented programming. It's the most popular style of programming there is, right? Although it's pretty common to try not to program object-orientedness in object-oriented programming languages. Like, for example, in 162, a lot of what I'm doing is I'm trying to avoid objects at all costs in the class about learning how to use objects to make data structures, but that's for your own benefit. Object-oriented programming kind of missed the mark in what it wanted to achieve. Still very valuable. Java is an object-oriented programming language. Python kind of is both. You can do objects or not. It doesn't really matter. There's nothing wrong with extending concrete classes, but often it's really going to cause problems. In practice, it's usually a bad idea. So here's a common example. The joke of this too is, and I'm guilty of this too, because I used to use this example. But the example I'm about to show you is a cliche example of how to use inheritance correctly in your typical 162 class. But if there is a Wikipedia article, except it's called ellipse circle, whatever. There's a Wikipedia article about how this is a stupid, bad example. There's a wiki article about how dumb this is, and yet most places you find it. So a classic example is ellipse circle. Oh, okay, a circle's a special case. So really, it's more, okay, we can talk about a rectangle square. We can make a rectangle class. We can make a concrete rectangle class. Easy peasy, right? It's got a length, it's got a width. Maybe we have some getters, whatever. But we also have a square. And a square is a rectangle, but it's a special rectangle, right? It's more specific. So, because a square is a rectangle, we can make a rectangle class and then extend it into a square class. Make sense? Yeah. So we've got our rectangle, we've got our square. So we can make a rectangle class. Maybe it looks something like this. Rectangle, length, width, some basic default constructor. Then we got a constructor that takes a length and a width. We set it, get length, set length. We have setters here. Maybe we shouldn't, but we do, whatever. Get width, set width, get area in a toString. Cool. Nothing fancy. Cool. We could also make a square, which extends a rectangle. Now, here, what we would do is, this is something you can do, is you say public square, you call the superclasses constructor, right? So basically, just call the rectangle's default constructor. That's fine. It creates a square. Great. Public square double side, well, you just call the superclasses constructor, but where you give it a side is the length and the width. Yeah? Cool. Get side is a new method we have to use, right? So we're not overriding. We're creating a new method called getSide. And all it does is return the result of getWidth. Okay, we could have used getLength because they should be the same if it's a square. You'll also notice, by the way, that this class doesn't have the length or width fields. This is common, right? This is kind of the whole idea of separability there. Set width, or set side, and then a toString. Cool, cool, cool. If I do that, I should still update. There's a problem here. I should still update whatever. This is not, there's a potential bug here, but it's not important for the demonstration I'm about to make. So this seems great and all. We can inherit getLength, getWidth, getArea. We override the toString because we don't want to say rectangle. We want to say, okay, it's the square. Hijack the superclasses constructors. Great. It's used in a similar way as like this is, but for the parent classes. Now, there's this idea called like Liskov's substitution principle. Basically, functions that use pointers or references to base classes must be able to use objects of derived classes without knowing it. There's this design principle for software called like solid, and this is actually a huge part of it, the L part. This basically means if I am a function that has a reference to a rectangle or a square, I really shouldn't give a shit if it's a rectangle or a square. Okay? So double area is a method that will double the area of the rectangle. So let's say I write a method called double area, and it takes a rectangle. Okay? Rectangle.setWidth to be 2 times its width. Okay? We double the area. Think of what would happen if I run it like this, though. I call it on the square. Since square inherits from the rectangle, it's entirely valid, right? Because double area expects a rectangle. A square is a rectangle, so we're happy. But the code will cause the square to have an unequal length and a width. Thus, the square no longer is a square, right? So we could fix this by saying setWidth, by saying, okay, super.setWidth, super.setLength. We can fix it. What happens if we now call it like this? Well, now the length and the width are equal, but this will cause the square not to double in size, but quadruple in size, because we doubled the length and the width. Long story short, it gets a lot more complicated. That's the point I'm making, is, okay, to fix this, we got to do this. And then to fix this, we got to do this. Okay, well, we can actually check. If a rectangle is an instance of a square, we do it this way. Otherwise, we do it. Or we just don't do that, right? Because we've made, in the spirit of using objects and inheritance, where we get no real value, we've made our code far more complicated. The point of this little lecture here is that you're supposed to go like, yes, you're correct. Long story short, keep it simple. I go on to say, it gets even worse. Yeah, it does. Cool. All right. Any last questions before we go on to implementing bags? No, nothing? Everyone's happy? Is the course moving too fast or too slow? Is it too easy, too hard for you? What do you say? Raise your hand if it's too easy. Raise your hand if it's too hard. So. Raise your hand if it's in the middle. Yeah, so usually what that means is when you ask students if it's too easy, you never listen to them. If they say if the speed is okay, that usually means it's too easy. And if they say it's too hard, that means it's just about right. So in other words, it's too easy. I need to challenge you more. You're too smart for your own good, geez. All right, I can make it harder for you, don't worry. I'm teasing you, don't worry. All right, bag implementations. I know, you're like, oh no, no, I'm teasing you. All right, given the definition of a bag, you have a question?
You're going to make it harder by not asking the same question for the 4th time in the final.
Oh, what a great question. For those of you that didn't hear the question is, are you going to make it harder by not asking the exact same question you asked 4 times already? on the final. I don't know. It is always funny when I'm like, okay, can you do a linear search yet? And people are like, oh yes, the hardest question. How would I know this would be on the test? All I've said, all 161, that one really burns me up in 161. Because after they'll be like, he never lived. All I say, all of 161 is, if there's one algorithm to know, it's linear search. That's the one. And then students are like, what could he possibly ask us? I have no idea. All right, anyways, thank you. I had a good laugh. Thank you very much. I don't know yet. I haven't written the test. We'll see. All right, anyways. You made my day. Thank you very much. All right, back to focusing. Okay, given the definitions of bags, and specifically the two very specific implementations, the index bag and the sorted bag, how can we implement these things? Well, we can have an array-based implementation. We could have a link-based implementation. We can have an implementation based on whatever container we want, really. But, we've been talking about array and linked ones, so let's talk about an array one. So, an array implementation idea. So, let's say we got a bag. I guess right here I'm saying it's neither a sorted bag or an index bag, but we just have some bag. All right? So, it's like the array stack or the array queue. But unlike the array queue, we're going to make it such that index 0 will always be the front of our bag. Okay? Now, so this is like idea 1 of the array queue, which we talked about was a stupid idea. And it's a stupid idea because, like with bags, adding and removing can happen from anywhere, right? So we got all fancy, like the DQ, in the DQ with the array, we wanted it to be constant time, right? So we shuffled everything down. Well, that was a problem because that made it linear time. And that's where the problem was, right? But now I'm saying, no, we're going to make it fixed to index 0 being the front, and we're going to do that shuffle every time, which means the removes are going to be linear time, which sucks because we just went from having constant time remove. But remember, the only reason we were able to get away with it is because of the constraints on how the queue worked. When you remove, it always comes from the front. Here, when we remove, it can come from anywhere. It could come from the front. It could come from the middle. It could come from the end. There's going to be a gap potentially anywhere that we create, and there's really nothing we can do about it. So at the end of the day, we're already doomed to have a linear time remove. So getting fancy with a circular array, that's not going to do us any good if I have a bag, A, B, C, D, and I say remove the C. Because I can do that. It's a bag. It's general. Okay, remove the C somehow. No circular array is going to solve this problem, right? Can't do anything about it. It's stuck. We got to close that gap. We got to go, okay, copy the D over, copy the, and so on and so on and so on until we fill that gap. Yeah.
You always just add to the first empty index since we're
But
really generic here.
if it is a very basic bag, you've got a good point. But then we would need to search for the first empty index, right?
No.
Which may not be that bad of an idea, but if it's a general add where it's an append, I always know where to... I like what you're thinking, but no free lunch. There's always kind of like a, okay, we could do that, but then how are we going to keep track of all this stuff? Maybe extra bookkeeping or a linear search. So that cost comes from somewhere. So yeah, with bags, adding and removing can happen anywhere. So adding to the middle would require linear time operation to make move, and removing from the middle requires a linear time operation to close that, no matter what. And that problem didn't exist before because of the special properties of the stack and the queue. Where with the stack, it always happened at one end, and the queue, it happened on both, but only one or the other, removing from the front, adding to the back. Because of that, we exploited something about it to get more, better computation times out of it. Here, because it's more general purpose, which is good, but it comes with a cost. Always linear time operations. Okay. So yeah, the expand capacity. We're still going to need an expand capacity, but here we don't need that fancy expand capacity like we needed with the array queue, right? Where we would have to loop back around because it's a circular array and all that. We don't need to deal with that because the front is always going to be index 0. Okay, yeah? So the functionality of a bag, regardless of the specific type, is going to need an add, remove, contains, count, is empty, size, and iterator, which again, more on the iterators soon. But we got to implement these things no matter what. But if we were to go and make an array indexed bag, we also need to implement add, that takes an index and the element, remove. You might say there's already a remove. Yes, but there's a remove that removes an element of type T and returns a Boolean, where this remove takes an index, int, and returns something of type T. Now, an interesting thing that can happen here is, like when you call a method, when you define it, you specify the return type. But when you call it, you don't specify a return type. So imagine I had remove. And I call it my bag dot remove 55. Which of these removes did it call? Did it call this one? Or did it call this one? The bottom one. How do you know? But the type T could be an integer. Ooh. Don't worry, it's usually pretty easy to address this problem, by the way. But, be aware that, that could seem ambiguous, right? But we could actually, it's not too bad, right? We just basically exploit the fact that this one's going to be an object. And so we can, kind of cheese it to be like the object integer this. You'll see. But be aware that this peculiarity does come up. Okay, array index bag. So for brevity, only a subset of the methods are included below. If you go and download the array index bag class from right there, you will see the full implementation. But let's talk about some of the implementation here. What are you doing? Who's he bugging? You? No, he's making faces at somebody. Oh, okay. What's up?
So if the bottom function if the bottom method wanted an integer rather than an int, everything would explode.
That would definitely be a weird situation.
Would.
Yeah.
Would
I'm not 100% sure how it would resolve it because I just avoid it at all costs. Yeah.
Okay.
But that is a peculiarity, yeah.
Okay.
You'd have some ambiguity. I'm not sure how it's resolved. So yeah, okay, for brevity. And, well,
Java, it probably just complains at you.
probably. Maybe, hopefully in a helpful way.
Yeah.
Now, we are out of time, so this is perfect. We'll pick up here on Friday. Any last questions? All right, you're all great. I'll see y'all, most of y'all, tomorrow in lab.